If p is an odd prime, k is a positive integer, and k square minus pk is a perfect square, can we find the value of k? The answer is yes. Let's do it. So if k square minus pk is a perfect square, then there exists an integer z such that k square minus pk equal to z square. Further, we assume z to be 0, 1, 2, 3, 4, so on. We rule out the case that z has to be negative because we can take z to be positive or 0. Now, we write this equation as k square minus pk minus z square equal to 0. Now you see that this is a quadratic equation. In general, quadratic equations are of the type ax square plus bx plus c equal to 0. And if coefficient ABC are integer, in this case that's the true, 1 is an integer, minus p is an integer, minus z square is also an integer, then this equation, further we are saying that k is an integer, this equation is having integer root, then it must follow that b square minus 4ac or discriminant equal to perfect square. Since k is an integer and k satisfies this equation, we must have that discriminant equal to b square minus 4ac is a perfect square. In this case, d equal to minus p whole thing square minus 4 into a is 1, c is minus z square, and that's equal to p square minus 4 minus plus, so plus 4 into z square. Since d has to be a perfect square, a perfect square, as d is a perfect square, there exists a positive integer m such that d equal to p square plus 4z square equal to m square. It is a perfect square, so m square. Further, you see that m has to be greater than or equal to p, and it is equal to p only if z equal to 0. Now, somehow we have to use that fact that p is a prime, so let's write p square in terms of m square and z square. So p square equal to m square minus 4z square. Further, a prime is having a few number of factors. If p is a prime, 1 and p are only factors of p. Let's factorize the right hand side. M square minus 4z square, that can be written as m square minus 2z whole thing square. So that's an expression of the type a square minus b square. That can be written as a minus b into a plus b. So p square equal to m minus 2z into m plus 2z. Further, we are assuming z to be non-negative. It may be 0, 1, 2, 3, 4 and so on. So we can say that m plus 2z is greater than or equal to m minus 2z. If you are adding something to m, that has to be bigger than you are subtracting something from m. So m plus 2z has to be bigger than or equal to m minus 2z. Further, m plus 2z are factor of p square, and the only factor of p square are, therefore m plus 2z has to be either p square itself or it can be p or 1. Again, m plus 2z into m minus 2z equal to p square. So if m plus 2z equal to p square, we are bound to say that m minus 2z has to be equal to 1. But what if m plus 2z equal to p? Then again we can cancel p out. So m minus 2z has to be equal to p. Lastly, if m plus 2z equal to 1, m minus 2z has to be p square. But you see that m plus 2z is bigger than m minus 2z. So it cannot happen that m plus 2z equal to 1 and m minus 2z equal to p square. This is not possible. So let's add those two equations. When we add to those two equations, plus 2z and minus 2z will get cancelled. So 2m equal to p square plus 1 comma p plus p is 2p. So from there it follows that m equal to p square plus 1 by 2 comma p. 2 gets cancelled. What about z? Let's write this one as equation 2 and this one as equation 3. So if we subtract equation 3 from equation 2, subtract equation 3 from equation 2, we obtain 2z and minus of minus 2z is plus 2z. So 4z, m will get cancelled. So 4z equal to p square minus 1 or 0. P minus p is 0. So z equal to p square minus 1 by 4 comma 0. Now you see that these are corresponding. Z equal to p square minus 1 by 4 when m equal to p square plus 1 by 2. Therefore we can write m comma z, the ordered pair m comma z equal to when m equal to p square 1 by 2 comma z equal to p square minus 1 by 4 when m equal to p, z equal to 0. Let us look at the easier case first, m equal to p and z equal to 0. But by equation 1, if we look at the equation 1, did we write equation 1 somewhere? Okay, we did not write. Let's write it here. Equation 1. We simply wrote equation 2. So, but by equation 1, k square minus pk equal to z square. And we got z equal to 0. So, k square minus pk equal to 0. Now, it cannot happen that k equal to 0. We are given by the equation that k is a positive integer. We take k common from the left hand side. K into k minus p equal to 0. But we are given as per the equation that k is a positive integer. K belongs to g plus. So we must have that k minus p equal to 0 or k equal to p. So in the easier case, we obtain that k equal to p. So m comma z were equal to p square plus 1 by 2 comma p square minus 1 by 4 and p comma 0. In the easier case, p comma 0, we got k equal to p. What about the case m equal to p square plus 1 by 2 comma z equal to p square minus 1 by 4? By equation 1, k square minus pk equal to z square. That is k square minus pk minus z square equal to 0. Once again, this is a quadratic equation. Roots are given by k equal to minus of minus p plus minus root over d, where d equal to b square minus 4ac. So minus p whole thing square minus 4 into 1 into z square divided by 2 into 1. But we see that we have taken d equal to m square. So instead of d, we can simply write m square. Therefore, k equal to p plus minus square root of m square. M equal to p square plus 1 by 2. So p square plus 1 by 2 whole thing square by 2 into 1 is 2. That's equal to p plus minus root and square will get cancelled. So we'll be left out with p square plus 1 by 2 by 2. Okay, we can take LCM and that will turn out to we then further multiply by 2 and we'll get 4 in the denominator. So 2p plus p square plus 1 comma 2p minus p square minus 1 by 4. So k equal to p plus 1 whole thing square by 4, or if I take minus common, p minus 1, right? P square plus 1 minus 2p, yes. P minus 1 whole thing square by 4, but with negative sign. But once again we are assuming k to be positive integer, so we ignore this case. So k equal to p plus 1 whole thing square by 4. But why is it that we are given p to be an odd prime? That's because we are taking m equal to p square plus 1 by 2. Now if p is even, that is the only even prime is 2, then p square plus 1 will be 5. 5 by 2 is not an integer, comma, since p is odd, comma, p square plus 1 by 2 is integer. So if p is even, this quantity p square plus 1 by 2 will not be integer. Is 5 by 2 is not an integer. That is the reason why we are assuming p to be an odd prime in the question. Further, if we assume p to be equal to 2, k will also be not an integer, but we are given k to be an integer.